So in this video, I will be explaining K nearest neighbor or KNN, its mathematical induction, code and implementing it from scratch. So first of all, why do we need KNN? Let's say we are given a new data point and we need to predict its category. So for example, let's say there are three classes, let the color blue represent class 0, red color orange represent class 1, red color green represent class 2. So when a new point is given, we need to predict its category. So it's based on the idea that similar things tend to be close together. So this point might lie to orange or green, as these are the classes which is close to this point. Another example would be like classifying email as a spam or not a spam based on the similar email. So let's get to the implementation of KNN. So first we need to define the value of K, or let's say we need to choose the value of K, which will be the number of neighbors. Then we need to calculate distance to all the training points and find the K closest neighbors. Then we will vote or take average depending on the type of problem we are dealing with, whether it's a classification problem or a regression problem. So for example, here it is a classification problem and there are two classes A and B and the new data point is given here and we are taking K equals to 3. So when we find the nearest neighbors while taking K equals to 3, we get 2 points from class B and a point from class A. So we can see that the maximum probability of this point is or in being class of B. So let's get into the implementation. So let's start by importing the necessary modules we require. So we require NumPy, which will be used for mathematical calculations or operations and handling the data efficiently. Then we require matplotlib for plotting the graphs as well as analyzing how KNN works. Then we require make classification and train test split for splitting the data set. Then we require k-neighbor classification, which will be used later on to test on different data set of load iris or maybe load breast cancer. Then we import accuracy score and classification report, which will be our evolution matrices to check how well our modeling is performing. Then we import counter, which is a Python library to count how it is working. In our case, we require it to count the neighbors. Then we import Seaborn for plotting the graphs more beautifully. So let's start with creating a toy dataset. First, we create a random seed 42. So what this does is that it ensures that every time our code run, we get the same random numbers. This makes our results reproducible so that anyone running this code will get exactly the same results as we get. So let's get into the creation. So first, we create a class 0 and we create the x coordinate and the y coordinate, then the labels. So how we are creating these x and y coordinates? So what this does is that np.random.normal generates a random number from a normal distribution. The parameters are 2 and it will be of 0.8 standard deviation and there will be 20 such points. Let me explain it once again. So what np.random.normal does is that it generates a normal distribution centered around 2 with 0.8 standard deviation and there will be 20 such points generated. So same will be done with class 1 and then we label the class 0 as np.0 for these 20 points and then we label the class 1 as np.1 of these 20 points. And then we combine these points. So here we concatenate the class 0 and class 1 x coordinates. Then we concatenate the class 0 and the class 1 y coordinates. And then with the help of column stack, and what column.stack does is that it puts these two rows as columns side by side. So it will create basically a feature matrix for the xtoy dataset. Similarly, we concatenate our labels into one array and we call it ytoy. So then we plot the dataset. So plot.figure does is that it creates 8 by 6 inches of the figure, which we can see here. Then what plot.scatter does is that it gives all the x coordinates with class 0 and the y coordinates of the class 0 and we color them blue. So these will be the x coordinate, these will be the y coordinates, and we color them blue and then mark them as circles and set its transparency to 70%, label them as 0, make its size 100, and we do the same with the class 1. So here we can see we have centered this around 2 comma 2 and we have centered this around 5 comma 5 using a normal distribution here with the random seed 42. So let's implement the distance calculation. So we create a function Euclidean distance and pass two parameters 0.1 and 0.2. So this one line returns the distance between these 2 points, the Euclidean distance to be more specific. So what it does is that 0.1 minus 0.2 give us the difference between these points, and then we square it, then we sum it, then take the square root of this point. So let's test for 2 points and here and pass it into the function, and then we get the distance between these 2 points. Now step 3. So now comes the core of KNN, finding the k closest nearest neighbors to any test point. So here we define a function get k nearest neighbor and pass 4 parameters, two of them which will be our training data set, then the test point and the number of points we need. So to implement this, we create a list, an empty list, distances, then we iterate through each training point and calculate the Euclidean distance using the function which we created earlier. Then we append this as a tuple into our list. Then what we do is we sort it based on the distance. Then we create another list and in which we only take the first k points, in which we take the only first k distances, which will help us to make a list named k nearest. And let's label it also. So now let's test our function. So I have taken a point 3 comma 3, which will roughly be between these two classes, and when we pass this point into the function, we get the top 3 labels or the top 3 nearest neighbors which are here. So 3 by 3 will be around here, so the closest one will be of this one. So now we will be implementing the voting system. Our voting function takes the list of neighbor labels as input, and here we will use the counter library which we had imported earlier, as it will help us to count how many neighbors are near it. This line returns the most common label. It might look a bit complicated, but let's break it. Vote count.most common one returns the one most common element as a list of tuples. Then 0 gets the first and only tuple from that list. Then again 0 gets the first element of that tuple, which is our predicted class. So let's test our voting system with the neighbors which we find earlier. So on passing the neighbors, we get the predicted class as 0, which can be clearly seen here. So if we take the point 3 comma 3, so it is more nearer to these points. So thus we get the class 0. So now comes the complete KNN implementation. So this function combines both the step of finding the neighbors and casting a vote. Step 1 does that, it finds the k nearest neighbors, and step 2 does the voting part and it returns the predicted class. And this function handles the multiple test points at once. We loop through each test point, make a prediction and store all the prediction in a list, then convert to a NumPy array. So now let's test it on our toy dataset that we created. So first of all, we split our dataset 70% for training and 30% for testing, and random state 42 ensures that we always get the same split in making our dataset more reproducible. We make prediction on our test set using k is equals to 3 neighbors. Then we run the accuracy test, which gives that our results are being accurate, and these are the predictions and these are the actual results which gives the prediction. So now let's visualize our manual KNN results. So let's plot a figure, creates a subplot, and first scatter all the points without our testing predictions. So here is the points that our training data set has. and before splitting. This is of before splitting. After splitting, these are the points which are in bold, which have been splitted, and the points which are in light color are which are of our training data set. So in the second subplot, first we mark the data set which are for the training purpose. Then after marking these points, we plot the points which will be our predicted points. So we plot each test point with its predicted color and correctness indicator. So you can see that the algorithm mostly correctly classify the test points, and the green edges show the prediction. Like here are the green edges which show the prediction. So now let's implement the KNN method using Scikit-Learn library onto our toy dataset first. Then we will implement the Scikit-Learn library on a real dataset. So first, from the Scikit-Learn neighbors, we import the K neighbor classifier, and let's take n equals to 3, and then we fit x train and y train into the Scikit-Learn model. Then we make the predictions on passing the x test, and then we get the accuracy score. And then we check the accuracy score of our manual KNN and the Scikit-Learn KNN. So we get that these predictions match. So now let's implement the KNN classification on a real dataset. First, we will load the iris dataset, which is a famous real dataset. The iris data contains the features, and the iris target contains the labels. This is standard convention in the Scikit-Learn library. X is for the features and Y for the targets. Iris.shape tells us the dimension of the data, and iris.features name shows us what column represents. These are the actual biological measurements. Iris.target name shows us the 3 species of the iris flower which we are trying to classify. And np.bin count how many samples, it counts how many samples we have of each class. It is important to check if our data set is balanced or not. Then we create a pandas data frame. For easier data exploration, panda.dataframe converts our NumPy array into a table with column names. So this line is a list comprehension that converts the numerical labels 0, 1 and 2 back into the species name. For each index I in Y iris, we look up the corresponding name in the target name. And iris data frame dot head gives us the top 5 rows of how our data look like. So now let's see the actual importance of the random state. So let's just split our data using random state 42, and let's see how it is reproducing. And then we do 2 splits without any random state, and then again 2 splits with random state equals to 42. Then we print the split. So here we can see that the accuracies are different for no random state, which shows that the data set which has been taken or which has been splitted were different. But if we take a random state 42 or any constant random state, we'll get the same split. So without setting random state, you get different train test split every time you run your code. This makes results unproducible. Setting random state ensures everyone get the same split and compare results fairly. So now let's train KNN and evaluate performance. So let's take KNN classifier with neighbors equals to 5. Then we fit the X train and Y train, and then we make predictions, then get the accuracy score and print it on the iris dataset. And then we also can print the classification report, which tells how is the precision, how is the recall, the F1 score, and many more things. So let us experiment with different K values. So I will be looping from range 1 to 21, and let's see how how it affects the model if on taking different values of K. So here is the plot. So we can see that for different values of k, different accuracy score are being produced. Here the dataset isn't too large, so maximum of the accuracy score will be similar, but on a very large dataset, the accuracy score will differ very much. So how can we fine tune the KNN performance? So for that, we need to choose the k value. For small k values, it will be sensitive to a noise, and for large k values, it will have smoother boundaries. And it also depends on what distance metric we are taken, whether we are taken Euclidean Manhattan or Minkowski distance. So for example, if we take k equals to 3, here the classification will give us as class B. But if we take k is equals to 7, it will give a classification result as class A. So what are the strength and weaknesses of KNN? So strength is that it is simple to understand and it works well with a small data set. But the cons are that it is sensitive to irrelevant features, and it is computationally expensive for large dataset, and it doesn't perform well on large dataset. As we can see that if there are many classes and many data points clustered in a same point, then it will be very difficult to predict on the basis of the distance metric. So that's it for KNN